Okay, class, today we're going to jump right into the next section, solving radical equations. So to get a solution to a radical equation, the most important thing is to just get the radical portion by itself. So for example, if we have this equation which involves a radical, the only way that we're really going to be able to solve that is to first isolate this bit right here, and you'll see why. So we're all pretty good at algebra, so we know that we need to subtract 2 from both sides. That'll give us the square root of 3x minus 2 equals 4. And so you can probably see why that's a good idea, because then we can eliminate this radical by squaring both sides. If we square both sides, over here we'll just get 3x minus 2, and then 4 squared is 16. From there we can just solve. We can solve using the techniques that we already know. So the only new thing here is just if you get that portion with the radical by itself, you know how to solve from there. So we'll get, I'll actually add 2, excuse me. 3x equals 18, so x equals 6. Now, see where it says, be sure to check every solution? With radical equations, this is particularly important. In Algebra 1, you probably learned to check your solution just to kind of verify that you did your algebra correct. In this class, you're probably doing your algebra correct most of the time, but with radical equations, it's very important to check your solution, and we'll see another example later on that shows why that's so important. So let's just go back to where we started and make sure that x equals 6 makes sense. We have 2 plus the square root of 3 times 6. Instead of x, we'll put 6 minus 2 equals 6. So that's 2 plus the square root of 18 minus 2 equals 6. 6. So we have 2 plus root 16 equals 6. 2 plus 4 equals 6. 6 equals 6. Okay, so it's good that we verified our solution. Okay, let's just move on with another example. So this one involves a cube root, but again the idea is the same. We simply need to isolate that part involving the cube in order to solve this problem. So, just using our simple techniques of algebra, recall with an inequality, when you divide by a negative number, the inequality actually switches directions. Okay, so this is what we want. We want an equation, or in this case an inequality, which has the radical portion completely isolated. Because then we can take all of this to the third power and do the same on the other side. So sort of, that eliminates the problem of the radical. We can transform it into a form which we know how to solve. So if we take away 8 from both sides, that gives us 133, negative 133. Divide both sides by negative 2. Dividing by a negative again, we're going to flip the sign. Let's just leave that as 133 halves. And then again, let's just check our answer to make sure that works out. So let's go back up to the top. If we put in 133 halves for x and it's multiplied by 2, that will give us 8 minus 133 underneath the radical. 5 minus 2 cube root of 8 minus 133 is less than 15. 8 minus 133 is negative 125. The cube root of negative 125 is negative 5. So we have 5 plus 10 is less than 15. So as long as x is less than 133 halves, then this will be a correct inequality. So it's good that it's always good to check. Okay. Let's just dive right into another example. This time we have 2 times the quantity x minus 2 to the 2/3 power equals 50. So again, the goal is the same. This portion involving our rational exponent is what we want to isolate. So we can start by dividing both sides by 2. We can get x minus 2 to the 2/3 equals 25. Okay, now remember from our last lesson, 2/3 power, that means we have the cube root of x minus 2. We're taking it to the 1/3 power, in other words, and then to get to the 2/3 power, we're going to square it. Right, so to the 2/3 power is like squaring a cube root. Okay, so we can take the square root of both sides. Right, if something squared equals 25, the thing itself must equal 5. And now we've got our target has been reached, our target to get the cube root portion isolated. So we can simply cube both of these things, get x minus 2 equals 125, which means x must equal 127. And then if we look back at our starting place, if we put in 127, 127 minus 2 would be 125. 125 to the 2/3 power would be the cube root, 5 squared, 25. So we would have 25, 2 times 25 equals 50. All right. Let's just keep it going with the examples here. This time we're going to have to the 3/2 power. Okay. First thing we want to do, obviously, would be add 8 to both sides, which would give us negative 189. If we divide both sides by 7, 189 divided by 7, -27. Negative 27 on this side, and here we just have the portion which includes the rational exponent. So again, the 3/2 power, we can rewrite that in a radical notation as the square root of 2x plus 8, all of that cubed, and that's still going to be equal to negative 27. So then we can take the cube root of both sides to deal with this portion, which would give us simply the square root of 2x plus 8 equals the cube root of negative 27, negative 3. And now we're ready to square both sides. If we square both sides, 2x plus 8 equals 9, 2x equals 1, x equals 1/2. Okay, let's go back and verify our solution. Okay, we have x equals 1/2, so that's what we'll put up here. 2 times 1/2 is 1, plus 8 will give us 7 times 9 to the 3/2 minus 8 equals negative 197. Right, just take 1/2 into x. 2 times 1/2 is 1, plus 8, 9. That's what's going to be inside our parentheses. 9 to the 3/2 power, that'll be the square root cubed. So 3 cubed, 27. 7 times 27 minus 8, does that equal negative 197? That's what we're asking. 7 times 27 must be 189, like we said earlier. 189 minus 8. Doesn't look like it. Looks like we have 181 equals negative 197. So that's not true. That's not true. So it's a good thing we checked our answer. This actually, we're going to say no solution. No solution. Something went wrong in our solve. I mean, like algebraically we did everything correctly, but you can kind of see where you would expect a no solution right about here. The square root of 2x plus 8 equals negative 3. Right there, that might have lit off a red flag because a square root can never be negative. Recall the way that we defined this notation, this radical notation, as indicating the principal root. For a even index, like a square root, you're never going to get a negative number. So there's no possible x that would make this true. And when you square it, you end up getting x that would give you 3, which squared would also give you 9. But there's no such x that would give you this negative result. So this is the first example of why we need to check our solutions. Because sometimes, because of the method that we use to solve these problems, things can go awry. The name for a solution like this is called an extraneous solution. An extraneous solution. So when you're solving radical equations, you need to check for extraneous solutions by substituting your result back into the original problem and eliminating, when necessary, solutions that do not actually work. Okay, let's look at another example, just to keep it moving. This one, I'll do some graphing to show you exactly why extraneous solutions, where they come from. Okay, so again, our goal is to isolate the radical. The first thing we need to do is isolate the radical. So let's take away 5 from both sides. Get the square root of x minus 3 equals x minus 5. Now that we've isolated the radical, we're ready to square both sides. X minus 3 equals x squared minus 10x plus 25, which must mean, if we subtract these over, x squared negative 10x minus x negative 11x, 25 plus 3, 28. Let's see if we can factor that. 28 is 7 times 4 ought to do it. Negative 7 and negative 4, I suppose, would add to negative 11 and multiply to positive 28. Okay, so we have two possible solutions to check. We should check both of these solutions, x equals 7 and x equals 4. Okay, let's go back to our original equation. Let's see here. The square root of 7 minus 3 is 4. The square root of 4 plus 5, does that equal 7? 2 plus 5 equals 7? Yes. Okay, 7 looks like a good solution. What about 4? The square root of 4 minus 3, 1. 4 minus 3, 1, plus 5. Does that equal 4? That does not look like it equals, so we will eliminate 4. This was our extraneous solution. This is the solution that we desire. So quickly, I can show you on the graph, if you get out your graphing calculator, you can follow along with this, of how did we get this result of 4 when it's not actually a solution to this radical equation. What in our method produced this extraneous solution? Alright, so let me bring up my graphing calculator. Alright. Cool. Okay, let's make a graph. If we solve our original equation so that it's equal to 0, if we just move everything over, we can easily see where our graph crosses the x-axis, where it would be equal to 0. That would be graphically a way to find x. So in y1, let's put the square root of x minus 3 plus 5 minus x. Right? That's just solving this so that it's all equal to 0. And if we graph that, okay, here's our graph. And if we can calculate where it equals 0. Jeez. Okay. Put in our guess. So I don't know if you can see that, but it's telling me that x equals 7 when y equals 0. So that was the solution that we wanted, was to get x equals 7. Okay, so where did this x equals 4 come from? Where did that come from? So let's go back to our y. In our y2, let's put in this. Let's put in our cubic, or our quadratic, excuse me. Let's put in our quadratic equation that we got as a result of the solution technique that we were using. So let's graph this. X squared minus 11x plus 28. Okay, let's graph that. Right, so you see we've got our original radical function, and then we've got this quadratic function as well. So if you look closely at this quadratic, we've got our two zeros, x equals 7 and x equals 4. So it gives us one of the same zeros, but the way that we squared both sides here kind of transformed our original function into something new that's going to give us this extraneous solution. X equals 4 is not going to be a solution of our original equation, but because of this method of solution, it's going to give us a solution, well, it's going to appear to be a solution of this quadratic that we're using to model the solution for the rational function. So the quadratic will always give you the one that you want, this x equals 7, but it's also possible that it'll give you extraneous solutions. So that's why it's key to check, to verify all of your suggested solutions from your solution strategy. Go back to your original problem that you're trying to solve and verify that those in fact solve the problem. So that's just graphically showing you why that is the case. Okay. Okay, this right here is going to be our challenge problem for the day. So, if you're watching this at home, congratulations, pat yourself on the back. You did your e-learning day homework. Your reward for your studiousness is this challenge problem. So we're going to have 4 problems out of the book as an assignment related to this, and then also this problem as well. So try your best using the techniques we've talked about in this video to solve this problem. X equals the square root of 30 plus the square root of 30 plus the square root of 30. It's indicating nested square roots, ... on for infinity. So you have to be a little bit creative to find the solution to this problem, but I believe in you. If you show it to me on Tuesday, I'll give you a high five. Alright, let's watch a few more examples before we close the video today, just to be thorough. By now, you can probably start to sense the pattern that what we're going to do here is isolate the radical portion, square both sides, now if we get this equal to 0, we can solve it the way that we know how to solve a quadratic. Subtract x from both sides, subtract 7 from both sides. Let's see, that would be plus 3 minus 2 would give us a product of -6 and a sum of 1. So that must mean x is either -3 or x is positive 2. So again, recall, in this step where we squared both sides, we introduced the possibility of an extraneous solution. So what do we need to do? We need to verify or dispute each of those solutions by putting them back into the original equation. Okay, -3. -3 plus 7 is 4, so we have root 4 plus a minus a -3 would be plus a positive 3 equals 1. So is 7 equal to 1? No, it is not. So -3 must be an extraneous solution. Let's try 2. Maybe that'll work out better. 2 plus 7 is 9, so we have root 9 minus 2 equals 1. Is 3 minus 2 equal to 1? Yes, it is. So therefore, x equals 2 is the solution we want. X equals -3 was extraneous, so we'll eliminate that. You would say the solution to this radical function, this radical equation, is x equals 2. All right. You can try these at home on your own. I won't spoil them by showing you the answers. So if you need to pause the video, go ahead. All right, one more example. This one's going to be entertaining. Okay. In this one, we have a square root and a fourth root in the same problem. So a little bit different than the ones we've looked at so far, but let's recall our solution strategy of isolating the radical. So I think what I would suggest, let's get one radical by itself and the other radical by itself. We can isolate them both. Okay, what happens if we square both sides? What would happen if we squared both sides? Well, a square root squared is obviously itself. We can think of this as 5 minus 2x to the 1/4 power and then squared. So it would be to the 1/4 squared would be the 2/4 power or the 1/2 power. So if we're squaring a fourth root, we're left with a square root. So we'll say x plus 5 equals the square root of 5 minus 2x. So it looks like we need to square again to get completely rid of our radicals. So we have x squared plus 10x plus 25 equals 5 minus 2x. If you're really clever, I suppose you could have gone straight from this step, taking both sides to the 4th power. Taking both sides to the 4th power right away. That would have been a little bit trickier and possibly opening the doors for some mistakes. So I would recommend square both sides, square them again. Now we have a function that does not include any radicals, just a simply quadratic function that we know how to solve. We can solve it by adding 2x to both sides and subtracting x from both sides. Or subtracting 5 from both sides, excuse me. Let's see what x's we can get here. 20, that's going to be 10 and 2. Okay, so x is either going to be negative 10 or x is going to be negative 2. So let's go back and check those two possible solutions. Let's do negative 10. The square root of negative 10 plus 5, negative 5. Already a red flag. A square root of a negative number. Not going to be rational. Fourth root of 25 equals 0. So that doesn't look like it's going to work. We could have I root 5 minus root 5. It's not really equal to 0. That's a complex number. So it looks like negative 10 is throwing some red flags. Hopefully x equals negative 2 can bring it home for us. Negative 2 plus 5, root 3, minus the fourth root of negative 2 times negative 2, positive 4, plus 5, 9, fourth root of 9. Could that equal 0? Let's see, the fourth root of 9, that's the fourth root of 3 squared, which would be the same as the square root of 3. So root 3 minus root 3 does indeed equal 0, verifying one of our solutions and indicating the other is extraneous. So that was probably the trickiest one, other than the challenge problem, which I am confident that you can do if you believe in yourself and think creatively. Okay, so what to expect on Tuesday when we meet again, barring any more weather-related difficulties. On Tuesday, we will start with a quiz over 6.4 and 6.5. Actually, we'll start with some opportunities for you to ask questions over the homework, and then we'll have a quiz. I'm going to go ahead and post a solution key to Wednesday's homework assignment, just so that you can check yourself, make sure that you're doing it. I won't post solutions for this 6.5 assignment just yet, but if you want to ask questions on Tuesday, we can. Show me your challenge problem on Tuesday if you've done it. We'll also go over the quiz we took on Monday, over those two graphs. We'll go over that quiz, and then we'll take a quiz on Tuesday. And if we have time, we'll move on to composite functions, the next section. So the homework, I'll post this, but if you're watching this, the homework on page 395, just do numbers 16, 19, 23, and 35. And also the challenge. Okay, that's the homework, 5 problems. Make sure to check for extraneous solutions. See you on Tuesday. Have a great weekend.